Alright, man, hope you're doing well. This video I'm going to continue to think a little bit more about continuity. Continuity at a point, continuity on a closed interval, and continuity of a function. It's an important idea in calculus. So let's first start with definition of continuity at a point. So let's say point continuity. And we talked a bit about this before. And a function is continuous at a point, x equals a, if the following happens, really if and only if. The limit as x is approaching a exists, meaning from the right and left agree as x is heading towards a. The function at a exists. Remember, the behavior at a of a function is different than the behavior in a very tight neighborhood around a, i.e. the limit. And most importantly, those two values have to be the same. Okay? So we call that point continuity. If things around a point are unexpected, if the function is behaving consistently around a point and at a point, around being the limit as x is approaching a, at a point being f of a. Okay? So some discontinuities could exist, for example, in a function like tangent of x, right? Which of course is sine over cosine. Right? And so one in particular discontinuity would be at pi over 2, right? Since the function does not exist, the tangent of pi over 2 doesn't exist. Right? It gives us 0 on the denominator. Right? That's one reason. Also, if you recall, the tangent function has these nice little vertical asymptotes. Right, here a couple periods, 3 periods. And if you notice, here's my pi over 2 value. And so the limit as x is approaching pi over 2 for the tangent function does not exist either. Okay? So using either the fact that the tangent of pi over 2 does not exist, or the limit does not exist as x is approaching pi over 2, because we get plus or minus infinity from the left of pi over 2 positive infinity, from the right of pi over 2 negative infinity. Either justification is enough to disprove. All we need is one continuity at a point. We call that a point of discontinuity, POD. Okay. Now, another idea is what's called continuity on a closed interval. On a closed interval from x equals a to x equals b. Right? Or you'll sometimes see it written as this. Not very often, but same thing. Okay. What this means is that there are no points of discontinuities on AB. Okay? So any interval over which there exists no discontinuities is a continuous interval. Okay? We say that function is continuous on a closed interval. Okay, so take that same tangent function. So here is negative pi over 4. Here's positive pi over 4. Right, so the tangent function is continuous on that interval. Negative pi over 4 to pi over 4. Okay? There are no discontinuities. We have a nice smooth stroke of the pen as we graph. There are no points at which the limit as x is approaching a value disagrees with the function at that value. Okay? And finally, we have this notion of continuous function. And a continuous function is continuous for all elements in its domain. Now that's an interesting point, because if we go back to the tangent function has discontinuities at elements that are not in the domain. Right? So for example, pi over 2 is one of those discontinuities. But yet, pi over 2 is not an element of the domain. Okay? So technically, the tangent function is continuous function, even though it has an infinite number of discontinuities. Now, the reason it remains to be a continuous function is because all of those discontinuities, pi over 2 being one of them, are not in the domain of the tangent function. Okay. So let's consider this other idea. All right, we have a nice fluid graph here. It could be any function. And I want you to think about all the points of discontinuity that you see here. Okay, and justify why are they points of discontinuities. Okay, pause, think about it, write down, and when you're finished, press play. Okay, so you should have 2 points of discontinuity. -2, since the limit as x is going to -2 of f from the left is not equal to the limit as x is going to -2 from the right. Therefore, the limit as x is approaching -2 does not exist. And remember, in order to be continuous at a point, the limit must exist. Okay? And at x equals 3, the reason is, yep, just to verbalize, the limit as x is approaching 3. Oops. X equals 3 is also a point of discontinuity. Since the limit as x is approaching 3 of the function is 0, which is not equal to the function at 3, which is -1. Okay, and remember the limit as x is approaching 3 has to be the same as the function at 3, which is not the case here. Okay, function continuous everywhere else. Okay, one last idea. It's called the intermediate value theorem. Intermediate value theorem. IVT, intermediate value theorem. And what that says is the following. As long as a function is continuous, and many existence theorems in the calculus rely upon continuity on a closed interval, and oftentimes differentiability on an open interval. But for now, we're going to say if a function is continuous on a closed interval. Okay, so let's give a little visual. Here's A, here's B. Continuous on that whole interval. Okay, and it doesn't have to be increasing like this one is, but let's just suppose. Then, for all k in between f of A and f of B. So for all the y values between, there's f of B, here's f of A. Right? All those y values get hit. So here's f of B, the y value. Here's f of A, the y value. And all those y values in between must get hit. So there exists some C, and C lives somewhere between A and B. So C lives somewhere along the x-axis, somewhere over here. Oops. There must exist some C, which is an elementer on that interval, oops, from A to B, on the interval AB, such that f of C equals that k, right? For all k, really, for any k we choose. Here's k, the y value, c is an x value. Okay, in other words, as long as a function is well behaved, it must hit every value between f of A and f of B. Okay, as long as it's continuous on that closed interval. Right? Another way of thinking that is if you look down at your speedometer and you're traveling 30 miles an hour, and then you look later down at your speedometer and you're traveling 50 miles per hour, there must have been a moment at which you were traveling 48 miles per hour. There must have been a moment at which you were traveling 39 miles per hour, etc., etc., etc. Okay? It's got to hit every value between f of A and f of B, as long as it's continuous on that closed interval. Okay? All right. Have fun with the homework. I'll post it. Have a great day.